Hi guys. Okay, so here are your 5.2 notes for definition and end behavior of polynomials. So before you start taking notes, make sure you have this exact worksheet in front of you. If you don't, go print it off of the calendar. I would hate to see you write all of this down. Okay, a polynomial is a monomial or a sum of monomials. So let's make sure that we understand what monomial is. Don't forget, mono means one, poly means many. And for purposes, we're going to say meal, that part of it, the end of it, means term. So a polynomial is a term or a sum of terms. To finish filling in the blanks, all the exponents are whole numbers and the coefficients are all real numbers. And just what that means is that your exponents can't be fractions. Okay, they can be 1, 2, 3, 4. Whole numbers are 0, and then you're counting numbers. Coefficients are real numbers, so they can't be imaginary. Okay, so the first thing I want to look at is we need to define what degree is. And in this first example, I'm just going to go ahead and tell you, this is called a degree 0, and type is called a constant. It's easier to demonstrate degree in this second example. I'm looking for the term with the largest exponent. So this term actually has an exponent of 1, don't forget that, and that's the largest exponent. So this term determines the degree, it's 1, and you know that this creates a linear. That's called a linear. Okay, here's my degree of 2, so it's degree of 2, and it's called a quadratic. Here's a degree of 3. Notice I have a degree of 1 here, but I'm looking for the largest degree, which would be that 3. Here would be that 4. So this first one is a degree of 3, and it's called a cubic. And now we're looking at a degree of 4, which is called a quartic. Okay, so let's just real quick look at some different groups of terms and determine whether or not it meets our definition of polynomial. Okay, so in A, all of my exponents are whole numbers, all of my coefficients are real. So yes, this would be a polynomial. Another thing we need to look at is something called standard form. So we're going to look at B and we're going to talk about standard form. Standard form means I start with the term with the largest degree. So if I look at this second example, that term has a degree of 1. This is my constant, and that term has a degree of 2. So this term has to be written first. So this is going to be changed to g of x equals pi x squared. And then I'm going to go to the next term with the next highest degree, which is that 7x with the 1. And then my constant is going to be at the end. Is the square root of 3 a real number? Yes. Okay? Okay, so yes, this would be a polynomial. In this third example, remember, my exponents need to be whole numbers. A whole number is 0, and my counting numbers, well, that is not a whole number. That -1 is an integer, so this actually would not even be a polynomial. Okay, and let's look at this one. I have x as an exponent. Okay, x as an exponent is not a whole number, so that one also would not be a polynomial. Now let's go back to the polynomials and let's look at 3 things that are rather important. I need to know the degree. So the degree here, obviously this is my largest exponent, so the degree would be 4. So it would be called a quartic. Over here, remember we put this in standard form. The squared is the largest, so that's a degree of 2, which would be called a quadratic. And in the next 2, they're not polynomials, so I don't need to worry about them. Okay, the next thing that's very important is the leading coefficient. The leading coefficient is the number in the very front once I put it in standard form. So the leading coefficient is the number in front of this x4, which hopefully you all know is a 1. So my leading coefficient is a positive 1. And the leading coefficient here okay, is in front of my x squared, it would be a pi, positive pi. All right, before we continue with these notes, let's just talk about a few things. Let's make sure you understand that when I write f of x, that x is my input. And when I input that x, what comes out is my output. Okay? Got to remember that inside this parenthesis right here is going to be my input. That 3 is going to be my input. I'm going to input it into the x's to see what comes out as the y. When I'm evaluating, I'm looking to see what does this function do in respect to an input. Okay? And yes, we expect you to have this on your notes somewhere, so find a place for it. Okay, there are two methods of evaluating. You all know the first method. The first method is called direct evaluation. So I'm going to take this 3, and I'm just going to directly input it into those. So I'm going to get f of 3 equals 2, put in the 3 to the 4th, minus 5, put in the 3, minus 4, put in the 3, plus 8. Okay? And now I'm going to go ahead and put that in my calculator. And what I'll get is 23. So what this means is if I put in the x of 3, I get out the y of 23. It actually creates a point, right? If I substitute an x in here, it's like creating a table saying this is my x, this is my y, put a 3 in, I'm going to get 23 when it comes out. Okay, what I'd like you to do here is I'd like you to go ahead and input this. First warning, notice I am inputting into parentheses. You should get f of x, or not even x, right? F of negative 6 equals positive 149. And you're wondering how I got a positive and you got a negative, and it's most likely because of parentheses. Negative 6 cubed plus 8 times negative 6 squared minus 7 times negative 6 plus 35. Okay, that should give you 149. Okay, now let's look at synthetic substitution or synthetic evaluation. And what I'm going to do is I'm going to do synthetic using this number and this polynomial. Okay, so synthetic substitution is different, and this is very new, so pay close attention. Synthetic evaluation or substitution is like doing upside down, I don't know, it's something very new that you haven't seen. So copy this down. I'm going to put a big division sign, and I really need this to be enough for 2 rows of numbers, a number here and a row of numbers here. And I'm going to divide, I'm going to substitute with that 3. So I'm putting the 3 from in here on the outside. And on the inside, I'm going to put the coefficients of every single term. So the first term is the x to the 4th, so I'm going to put a 2. And then I have an x cubed. But notice I don't have an x squared in here. Okay? In synthetic evaluation, you must need a zero, leave a 0 as a space. I have a negative 4 and I have a positive 8. The first step I need to do is I need to bring that 2 down. Okay? So right here you should be writing notes. First step is bring 2 down. Okay. Now what I'm going to do is I'm going to start multiplying. So I'm going to multiply 3 times 2, and I get 6. And I'm going to put that 6 right here. And I'm going to add these 2 together, and I get positive 1. And I'm now going to take that 3, and I'm now going to multiply by 1. 3 times 1 is 3, and I'm going to put it in here. Add those 2 together, and I get 3. I'm now going to take that 3 and I'm going to multiply it by this 3. 9, put it here. I get 5 if I add them together. I'm now going to take that 3 and I'm going to multiply it by the 5, and I get 15. And if I add those together, I'm going to get 23. So when I input 3, what comes out of my synthetic evaluation is 23. Notice I get the same answer. I get the same answer using direct evaluation or synthetic evaluation. And in your head, you right now are saying, Mrs. Irwin, you're crazy. Why would I do all that work if I can just substitute it like we learned when I was in 7th grade? Well, because this synthetic evaluation, we're going to turn into something called synthetic division very soon. So you need to make sure you know it. All right, so let's try it again. I'm going to walk you through it one more time. So again, I'm going to do the upside down division bar. I'm going to use this polynomial over here and synthetic substitute the -6. So I'm going to substitute in the -6, and I have an x cubed, I have an 8x squared, I have a -7x, and I have a positive 35 constant. Notice there are no missing terms, so I don't need that missing 0. First step, I'm going to bring that 1 down. Has to be the first step. I now am going to start multiplying. So -6 times 1 is -6. If I add these two together, I get 2. -6 times 2 is -12. If I add those two together, I get -19. Last one, -6 times -19 is 114. I'm going to put it in here. If I add those together, I get 149. So again, if I input -6, I get an output of 149, thus creating the ordered pair XY. Now we're going to talk about something about end behavior, and the key word really is that word end. Okay, we're going to be talking about this a lot. This is also we can call curve sketching. The end behavior of polynomial functions graph is the behavior of the graph as x approaches either positive or negative infinity. Okay, and the two functions that I want to deal with are the line, and we know we have a positive line and a negative line, and the quadratic. We have a positive quadratic and a negative quadratic. And I want you to remember that this is y equals x squared, and this is y equals x. End behavior is determined by a leading coefficient and a degree. And what is end behavior? End behavior is, what are the ends doing? What are the ends doing? What are the end of this function going up? What is the end of this function doing going down? What are the end of this function going up and going up? So how do you determine the end behavior of a polynomial? You look at the leading coefficient and the degree. The leading coefficient here is positive. My degree is 1. Okay, so we're going to say the leading coefficient is positive and the degree is 1. And there's a statement that we always say, and the statement is, as x approaches infinity, so as x gets bigger, what is happening to my function? It is also approaching infinity. So as x approaches, this arrow is for approaches, positive infinity, f of x, the graph, is approaching positive infinity. Now let's look at the other side in this graph. As x approaches negative infinity, so as I start plugging in or inputting in more negative numbers, my function is also approaching negative infinity. So as x approaches negative infinity, my function is also approaching negative infinity. Okay, so that's the end behavior. If we move to the next graph, remember, since this is a negative, my leading coefficient is a -1 and my degree is still 1. So my leading coefficient is -1 and my degree is 1. And we're going to look at end behavior again. As x approaches positive infinity, my graph is actually now approaching negative infinity. So as x approaches positive infinity, the function is approaching negative infinity, or the graph. As x approaches negative infinity, so as my x is inputting smaller and smaller, my graph is going up to positive infinity, approaching positive infinity. Now let's look at the quadratic. The quadratic is interesting because both the ends are doing the same thing, right? As my x is getting bigger, my quadratic is approaching positive infinity. As x is getting smaller, my quadratic is also approaching positive infinity. So as x approaches positive infinity, my function is approaching positive infinity. Okay? Let me just real quick put in the leading coefficient here. We know has to be a positive. Okay, so the leading coefficient is positive because I'm opening up. We know that. This leading coefficient has to be negative because I'm opening down. And I do know the degree here is 2. So now let's look at the other side. As x approaches negative infinity, my function approaches positive infinity. And when I move over here, I know that my leading coefficient is negative, and my degree is still a quadratic, so my degree is still 2. But what happens as my x approaches positive infinity? So as my x is getting bigger, my function is actually getting smaller. So as x approaches positive infinity, the function is actually approaching negative infinity. And it's the same on the other side. As x is getting smaller, approaching negative infinity, the function is again approaching negative infinity. The only thing is, y'all know that we don't have just a degree of 1 and a degree of 2. We have degrees 3, we have degrees 4, we have degrees 5, we have degrees 6. So instead of saying degree 1, we are now going to change this to an odd degree. So for all odd graphs, my end behavior, no matter what it looks like in the middle, the ends, one's going to go up, one's going to go down. That's going to be a positive. Same thing over here. Okay, that's going to be a negative odd graph. Okay, down here on the bottom, I know I have 4s or 6s or whatever you want to call it, but they still will open up. So instead of saying degree of 2, I'm going to say an even degree that's positive. And over here, the same thing. Doesn't matter what happens in the middle, but both of my ends will be doing the same thing. They will both be pointing down, so I am negative. So I can't just say this is a degree of 2. I'm going to say this is for all even degrees. So take these two graphs, for example. I need to know if the degree is odd or even, and I need to know if the leading coefficient is positive or negative. So odd or even, positive or negative. Same thing over here, odd or even, positive or negative. Okay, well, I know they're both, this is opening up just like a quadratic, so I know that it has to be positive. I also know that this opens up like a quadratic. Both ends open up. A quadratic is a squared, which is an even number, so this has to be an even. It's not going to be a squared. It could be a x to the 6th. I don't know, but it's going to be an even. Okay, in this next example, I know I have something that is kind of like this, and if I were to put a negative, let's just draw a negative line, okay? The end behavior of this is just like a line that has a negative slope. So I know that this guy is negative, okay? I also know that a line is y equals x to the 1st. So this would have to be an odd degree. On the last two graphs of your notes, I would like you to try to draw a graph of the first one that is odd with leading coefficient of positive, and a second one that's even with also a leading coefficient that's positive.